Today, we're going to be talking about chapter 13. So we're going to kind of continue talking some more about polynomials, though this a little bit more in an algebraic sense, a little bit deeper than we did in chapter 12, where we just kind of touched on some basic vocab stuff. So we're going to start off with two pieces of vocab that should be familiar with us or to us. First is extrema. When we talk about the extrema for a graph, what are we talking about? So if we're talking about the extrema for a graph, what are we talking about there? Yeah, just like high points and low points. Not necessarily the highest, but relative high points and low points. Okay. And the other piece of vocab here to start with are the zeros. What are the zeros for a graph? What are the zeros for a graph? When we talk about the zeros for a graph, what are we talking about? It's the same as the Xintercepts. So just the places where the graph crosses the x-axis. So if we asked you guys to locate the zeros in extrema for the polynomial x cubed minus x, what would we want to do? Yeah, we'd start by drawing the graph. So we could use our calculator to do that. Would output something that looks like this. So based on that picture, we should be able to tell the zeros really easily. What are the zeros? Yeah, so -1, 0, and 1. Just the x-intercepts. How about the extrema? Do we see any extrema here? Oh, I see one in there. And I see one down there. The one on the left here would be called we call that kind of extrema. Okay, what kind of max? Local, because it's not the highest overall point, right? There's lots of points over here that are higher. And the one on the right is a local minimum. Again, it's local because there's lots of points over here that are lower. So if I wanted the coordinate then for those extrema, can I get it just from the picture? No. What else would I do to get that? Yeah, use my calculator. So I could just go ahead and type in this friendly old guy into my y equals menu. And we'll just, I have a weird thing in there, so I'm just going to zoom standard it. Okay, it's not a very helpful picture. Maybe we'll just go -2 to 2 and go like -2 to 2. There we go. That looks pretty similar to what we had before. So let's say we want to find this one first, the local max. Where do I go to find that now on my calculator? Do you remember? Press second and trace. And from this list of commands, what sounds like the one that I'm going to be interested in? The maximum command, because we're looking for a local maximum right now. So the local maximum is going to ask us 3 questions. It's going to ask first for a left bound. So to give it a left bound, I'm just going to move my cursor so that it's on the left side of that local maximum. That looks good right there. And then press enter. Now it's going to ask for a right bound. So I'm just going to again move my cursor so that it's on the right side. And then press enter. And then asks for a guess. That doesn't really matter. I'm just going to press enter again. So I get -577, 385. And I could repeat the same process, but this time using the minimum command. And then I'd get +577, -385. Everybody okay with that? We've used that command a bunch of times first semester already with the calculator, right? So hopefully you remember using that. And probably last year in Algebra 2 class as well. So here's a quick question. Does anybody notice a relationship between the degree of the polynomial and the number of zeros? So the degree is 3, and the number of zeros is 3. Okay. How about a relationship between the degree and the number of extrema? The degree is 3, and how many extrema do I have? 2, right? I have a local max and a local min. So what might we think is the relationship between the degree and the number of zeros? In this example, we saw the degree was 3 and the number of zeros was 3. It's the same. Okay, almost correct. How about a relationship between the degree and the number of extrema? It's different by how much? 1. Almost. So what's the almost part, Mr. Kulik? Well, it's that the degree will be, or the number of zeros will always be at most equal to the degree, and the number of extrema will be at most 1 less than the degree. So it could be less, right? So just to kind of illustrate that, let's say we have the function f of x equals 3x to the 4th minus 5x cubed plus 2x plus 2. And we want to ask how many zeros could there be and how many extrema could there be? So I'm going to start by first observing what the degree for our polynomial is. The degree here is 4. Again, just the biggest exponent on a variable. So how many zeros could there be? So 4 is not correct because you're missing something. Yeah, it needs to be at most 4, right? What does at most 4 mean? Means you could have 0, 1, 2, 3, or 4 zeros, right? It's not clear just from that it has to be exactly 4. It just could be up to 4, up to and including, I should say. So either way of writing that is fine. If you ask me, I'd rather write the at most than write that whole list out, but they're both correct. How about for extrema? What would I say there? At most 3. Very good. And again, you could have also written it as 0, 1, 2, or 3. Right? Either answer is fine. There's no preference given. We feel okay using that theorem? Very easy, right? And will end up being quite helpful. Another piece of vocab here. That's going to be end behavior. Does anybody remember what end behavior is describing? This would have been something we talked about last year in Algebra 2 class. What do you guys think? Do you remember what end behavior is? So the end behavior is just basically describing what the arrows are doing on your graph.
Is that like the positive infinity?
Oftentimes infinities are involved with this, sure. So what we're going to be using here, we're going to use a specific notation involved. It's called limit notation. So let's just kind of do a quick example to show you what limit notation looks like and how to translate a picture into limit notation. So let's say that this is my graph. How many arrows do you see on this graph? 2. So I'm going to have an end behavior description for that arrow and a different end behavior description for that arrow. So if I ask you to describe what the blue or the arrow that I've circled in blue is doing, how would you describe that? How is it pointing? Okay. I'm going to always describe, when I do this though, instead of saying down and to the left, I'm always going to describe like the horizontal part first and the vertical part second, just like x comma y we always describe a point. So we're going to describe the arrow points left and down. So the left part, the way I'm going to write that, is I'm going to write the letters L-I-M. That's short for limit. And then x approaches negative infinity. That's just how we write left in limit notation. Then we write the name of our function. Oh, I guess I should have given this function a name, huh? We'll call this y equals f of x. And then to describe down, we're going to write negative infinity. Ava?
So can you explain again how you said that the x and the arrow represents going left?
Which way are the negative values on the x-axis? To the left. That's why limit as x approaches negative infinity is talking about the left side of our graph, because that's where the negative numbers live.
So
Or
if it's going right, it would just be x approaches positive.
yeah, that's exactly right. So if we want to describe the arrow that we've circled in green, we'd say that arrow points right and up. So to describe right, we're going to say the limit as x approaches positive infinity. And then we'll write the name of our function, f of x equals. And then to describe up, we're going to write positive infinity, because that's where the positive values on the y-axis live, are up. Is everybody okay with how I translate a picture into this limit notation? It's pretty easy, right? Now, is that the only way that I can figure out a limit notation? No, I could generate a graph as well. Or not a graph, I'm sorry, a table. So for example, if I had this function and I had this table, what I'd want to do is I'd want to look at how the x values are changing. My x values go from 100 to 1,000 to 10,000. What's the overall pattern here that's going on? Well, I mean, they're getting bigger, right? So that tells me that the x's are going towards positive infinity. And then if I look at the y values, what do you notice that are happening there? They're getting bigger. So it must equal positive infinity. Is everybody okay with how I took the information on that table and came up with a limit notation for it? I just looked at whether the x's were getting bigger or smaller, and then looked at if the y's were getting bigger and smaller. Just like I kind of do with the graph, right? And then let's say that I generated some values or use some negative values for x. Again, what I notice here is what's happening to the x's. Getting smaller each time, right? From negative 100, negative 1,000, negative 10,000. So x is going towards negative infinity. And then let's look at what's happening with the y's. They are also getting smaller. So we have that. The y's are going to negative infinity. Is that okay there? Now, Mr. Kulik, you just like threw this table up here and acted like I would know how to generate that table, right? Well, it's really easy to do that. In fact, we already kind of know how to do it. What I'm going to do is I'm going to start by just typing in the name of my function. Oops, it's the plus sign there apparently. And then we'll exit back out. And what I'm going to do is I'm going to plug in the value 0 or 100, and then 1,000, and then a 10,000 to generate those values. How do I do that again? Plug something into the y equals. I use that y1 command, which is located in the vars. Yep. So I'll press the vars button, then what? Y vars, and then function, and then we'll do y1. So if I would do like y1 of 100, there's that 1,959,901. If I press second and enter, it'll just bring back up the same thing I have, and I can just update that by adding a 0 and a parenthesis. And there's my like 1 trillion and change. And second and enter, and I can just update that again by tacking another 0 and closing the parenthesis on, and there's that guy. Does that feel okay? On how I generated the table now? Now, is there anything magical about these numbers 100, 1,000, and 10,000? No. I mean, they're just like nice, even round numbers. Could I have done like 257, 13,986, 214,892? Yeah, that would be fine. They're just like progressively getting like orders of magnitude bigger. That's fine. Those would be okay numbers to do. I don't know why you'd pick such really specific, detailed numbers, but like you could do that. Me, I'm just going to continue to pick like easy round numbers that are nice to plug in. You know what I mean? But there's nothing magical about those numbers that I picked. Okay. That's the first section. So we've talked about finding zeros graphically, right? What if I want to start doing that algebraically? That's going to be the main push for the rest of this chapter. So if I want to solve this, or I want to find the zeros here algebraically, the 0 is the same thing as an x-intercept, correct? What's the y-coordinate of any x-intercept? Zero, because it's on the x-axis. The y-coordinate has to be 0. So all I'm going to do is I'm going to start by replacing my f of x with a 0. So far, so good. Now, to solve this equation, what's the first thing I look for? Well, I mean, sure, but are there any like terms? So there's no like terms to combine. What else would I be looking for? A greatest common factor. So that's right, Elise. If I look at the terms here, each term contains a factor of x. So I can factor that out. And if I look at what remains, that should be something that I recognize. Oops, I have a little mistake here. This should be a plus. There, by mistake. Apologies. What is that thing in blue there? That's left. What do we call that? Starts with a Q. Say quadratic polynomial, right? X squared minus 6x plus 8. What do you know how to do with quadratics? It's the one skill you've told me over and over again that you learned how to do last year in Algebra 2. The other F word. Factor. Not that F word. Ha ha ha. That was a cursing joke. Thanks for your pity. Do you remember how to factor something like x squared minus 6x plus 8? Okay, what do you have to, what's the number you have to multiply to get? Okay, what number is the add to get? Okay. What do I start with? The multiplication part or the adding part? Multiplication, that is a finite problem. The addition problem is infinite. We don't want to start there. What are the numbers that multiply to give us positive 8? Okay. And that's the pair that we need, right? That'll add to give us the negative 6. There are others, but that's the pair that we want, so we'll cut straight to the chase. Okay, since the leading coefficient is 1 on my x, that allows me to go straight to the factored form. Now let's think about what we have here. We have 3 things that are being multiplied together and are equal to 0. What can I say about a situation like that where I have things that are multiplied together and I get 0 out of them? It's the only way to get 0 in a multiplication problem. Is one of the things you're multiplying is by 0, right? So this is true whenever any of the factors is equal to 0. Now x equals 0, that's already solved. X minus 2 is equal to 0. Well, I'll just add 2 to both sides. X minus 4 is equal to 0. Add 4 to both sides. So how many zeros did I find? 3. What's the most zeros I could have found in this problem? 3, because that's the degree for the polynomial. So do I know I found them all? Yeah, because the number of solutions match the degree. I know there can't be any more. I found them all. Yay! Okay, let's do another example. Find the zeros and the multiplicity of the zeros for the function f of x equals x cubed plus 6x squared plus 9x. Do you remember what multiplicity means? Okay, then we'll just worry about that at the end. Let's find the zeros first then. Sound good? Okay. What do you start by doing? Changing f of x to 0. Sure, that sounds good. Then what? Take a look for a greatest common factor. We see that each term includes an x. So we can take out a greatest common factor of x. Good. Then what? Okay, factor. How does x squared plus 6x plus 9 factor? So the two numbers that multiply to give us 9 and then add to give us 6 are 3 and 3. So we'll write that as x times x plus 3 times x plus 3. I then apply the zero product property, which allows me to set each of the factors equal to 0. X equals 0, that's already solved. If I subtract 3 from both sides, I get negative 3. And subtract 3 from both sides, I get negative 3. How many solutions do I have? 2, right? What are the two solutions? 0 and negative 3. How many times does 0 occur? Just once, right? So its multiplicity is 1. How many times does negative 3 occur as a solution? Twice. So its multiplicity is 2. Notice here, how many solutions did I have? 2. How many answers did I get when I solved this? Kind of got 3, right? Just one of them happened to be the same answer twice. But here's an example of the degree was 3. I only got 2 zeros, but there's still kind of 3 answers here, right? Everybody okay with that? Now, would it be nice to be able to predict by looking at a picture whether I should be expecting a multiplicity or not? Would you like that? Yeah, that'd be quite helpful. So let's talk about how to do that. So what I have here is a picture of 3 different kinds of x-intercepts. This first x-intercept, you see how the graph goes straight through the x-axis? We call that a straight. See this second x-intercept where the graph hits the x-axis and then goes back the same direction it came? We call that a bounce. And you see this other one where the x-intercept, it's like concave down until it hits the x-axis and it switches to concave up. We call that a bend. Now for x-intercepts that are straight, the multiplicity is always going to be 1. For bounces, the multiplicity is always going to be even number that's at least 2. And for bends, the multiplicity is always going to be odd, greater than or equal to 3. So if I have a bounce, the multiplicity could be like 2, 4, 6, 8. Not 9, because that's an odd number, but it could be 10. If I have a bend, the multiplicity could be 3, 5, 7, 9. Not 10, because that's an even, but maybe 11. So if we go back and we looked at this function that we just had, x cubed plus 6x squared plus 9x. And I graph that. Notice here I have my bounce at -3. And I have a straight at 0. Which matches what we saw here, where I have a 1 multiplicity solution at 0 and a 2 multiplicity solution at -3. Is everybody okay with that? This will become a very important piece of information as we go deeper into this chapter. All right. So at this point, all these solving problems we've done have been purely like algebraic, right? Let's do something that feels a little bit more like real worldy. So let's take a look at this problem here. We have that a company wants to create a cardboard box with an open top. The box needs to have a volume of 500 cubic inches and is to be created by cutting squares from each corner of a rectangular piece of cardboard in order to create tabs to fold up. So if you look at the figure we've drawn, the shaded parts are like the squares that we've cut out, and the dashed lines are like the perforations in which we'd fold up to make our box, right? Like a recycle bin. Has no top to it. Everybody's okay with the picture? How to visualize that in 3 dimensions? Okay. The piece of cardboard is 26 by 20 inches. What size squares should be cut from each corner in order to create the proper volume? Okay. So let's start just by writing down some of the stuff that we know. So we know the box has to have a volume of 500 cubic inches, right? And then who remembers how to calculate the volume for a box? Length times width times height is correct. Actually, I'm going to just write it like that. Okay. So in this case, I know that the length times width times height has to be 500. So far, so good? Okay. Let's label the length, width, and height for the box now. So this piece here would be like our length, right? That piece there would be like our width, and that piece there would be like our height. Does that feel okay to you guys? And just labeling our picture here? All right. What else does it give us? It tells us that the sheet of cardboard is 26 by 20. So I know like this side is 26 inches. And this side is like 20 inches. Is that okay with everybody so far? And then what is it that we're actually looking for? That size of the squares that should be cut from the corners, right? So I'm going to say that'll be my variable x. So that's just going to be the side length of the squares that are cut out of the corners. So I'm going to take my picture and label that now. Everybody's good with how I've labeled things? Okay. Now the tricky part. I need to figure out a way to rewrite length times width times height in terms of x's. So what I want to do is I want to write an equation that relates y and x together. Like that equation. See the stuff I've highlighted in yellow? What equation could I write from that? If I add up x plus L plus x, that's got to be one side of my cardboard sheet, the 26 side. Or if I rearrange that, I could say L is going to equal 26 minus x, or 2x. Okay. What else could I do? I can relate width and x by saying, yeah, or just that w is 20 minus 2x. And then my last one, what is h going to be? What equation can I write for h? Lucas, you're mumbling. You got it? No? Okay. Anybody? Isn't h just the same as that? All the squares we're cutting out of the corners are all the same size, right? It's just h is equal to x. That's it. Is that okay? So if we put this all together now, we have 500 equals, instead of length, I'm going to write 26 minus 2x. Instead of width, I'm going to write 20 minus 2x. Instead of height, I'm going to write x. So now all I need to do is solve this equation for x. What should I do to do that? Yep, got to multiply it all out. I would start by foiling those two pieces first. Let's see, 92, yeah. And then we'll just distribute the x back through. In order to solve one of these polynomials, what does it have to equal? 0. So how am I going to make it equal 0? Subtract 500 from both sides. Right? Now notice that I have no constant term on the right side of my equation, so I just end up with like a minus 500 at the end. So to solve this fellow, what should I do next? What do you want to do next? Okay, look for a greatest common factor. 4 would be it. Let's see. 92 divided by 4 is 23, I think. And then 520 is 130. And then 500 is 125. I notice because there's no variable attached by that 4, I can just divide both sides by 4. But I'm not really left with anything that's any easier to factor now, am I? I still have 4 terms there. Do we know how to factor something that looks like that? Nope. What are we going to do? Turn to a graphical method with our calculator. That's right. So we're going to go ahead and graph the function x cubed minus 23x squared plus 130x minus 125. Oops. So I'm just going to go ahead and type that into the y equals menu. And I'm going to choose a window here. So the x is representing what again? In my equation, what does the x represent? It was the side length for those squares, right? So what's a minimum for our side length for our square? It's the minimum value that a side length for a square can have. How about 0, right? Because you can be less than 1, right? You could be half an inch or something. And what's the longest that x could be? You got to think about the real life situation. Look at the picture. Why is 10 the longest that it could be? Look at this side here that's 20 inches. If this x is 10 and this x is 10, how much is left? 0 for that side. Any bigger than 10, you'd have like negative value for width, and that's clearly nonsense, right? Okay, what is the y representing now? Remember that 500 was the volume. What's the smallest possible volume that our box could have? Zero. I'm going to write negative 100 though, because I want to be able to see the x-axis. I don't want the x-axis to just be the bottom of my screen. What's the biggest possible volume our thing can have? 500 sounds good. And then I'll go by 50s or something here. All right. So here's our picture. What am I interested in? The x-intercepts. So I'm interested in this point and then that point. How do I find the x-intercepts? I press second and then the trace command. Which one of these sounds like the one I'm looking for? Isn't 0 the same thing as an x-intercept? Right, the zeros for that's the one I want. So 0. To do this, I need to answer 3 questions from the calculator. So first it's asking for a left bound. I'm going to look for this x-intercept that's over here that we can't see anymore because the word left bound is in the way. So what I need to do is I need to move my cursor somewhere on the left side of that x-intercept. What do I know about the y-coordinate for something on the left side of that x-intercept? It has to be negative. So I'm just going to be watching my y-coordinate here as I move my cursor and wait for it to get negative. So there we go. I got some negative numbers there. So I'll go ahead and press enter. It's now asking me for a right bound. So I'm just going to move my cursor till I have a positive y-coordinate. Press enter. And then I guess, and it spits out about 1.20. And then let's go find the other x-intercept. Same idea. So second trace, 0 command. This time the left bound should have a positive y-coordinate, right? Because we can see right before that x-intercept, the graph is above the x-axis. So that looks good. Press enter. Move to now I have a negative y-coordinate. I'm under the x-axis. Press enter. And then a guess is fine right where it is. I got 702. If I wanted to check these, what would be the best place to check these? I'd want to go back to this equation and see if I plug those values in for x, do I get 500 or pretty darn close to it? Will it be exactly 500? No. Why not? Yeah, because I rounded here. So, but they should be pretty close. What's going to be the easiest way to do that? Well, I'm just going to go ahead and put that equation into like y2 and then use the calculator to just plug those numbers in. I think that'll be a little bit more efficient than plugging each number in separately. So I'll do vars, y-vars, function y2 of 1.20. Almost 500 on the nose. And then 702. Looks pretty good to me. What'd you guys think? What's the hardest part? The setup, right? once we've gotten this equation, pretty much everything we could have, we could have just taken this, subtracted the 500 over, not even bothered to FOIL anything out and just used the calculator. Could have done that still, even at that point. But we didn't know from looking at it that we wouldn't have been able to do any factoring here. Probably we wouldn't have been able to. So maybe like I could have, but that's a different story. All right, this feels like a good place to stop. So at this point, you guys should be able to do up through 15 from the problem set. Once you guys take the last 20 minutes or so of class to work on that. And yeah, I'm good if you're good. Are you good? Okay.